Hi everyone, this is Michel Daher. So today I will be talking to you guys about improved casting manufacturing processes. So I worked on this project with Karim Abdallah and Mohammad Mir. To start off, I will be doing some background and motivation. So every single year in the United States alone, around 6.3 million fractures occur. Roughly 2.4% of people experience a fracture yearly, with the most common type being a wrist fracture. More generally, it is estimated that the average citizen in any developed country can expect to sustain 2 fractures over the course of their lifetime. Breaking a bone is an awful experience. Trust me, I know. But the experience doesn't end a day, a week, or even a month after the injury. Treatment is often an incredibly uncomfortable experience in and of itself and can last for many months. So, fortunately for us, bones can heal by themselves given enough time. However, while they can self heal, bones do need our help to do so properly. So, the purpose of treatment is two things: fast recovery rate and correct healing. So, to assist in the recovery rate, treatment aims to immobilize and support the bone to ensure an uninterrupted healing process. To assist with the correct healing, treatment aims to align the bones in the correct orientation so that when the fracture actually heals, the bone is correctly repaired. So, the most common treatment method that we have right now that is capable of doing both of these things is the orthopedic cast. And this will be the focus of our project. So, now we will be discussing the drawbacks of traditional casts. For one, these casts are rarely waterproof. Getting them wet can cause integrity loss, leading to breakdown of the cast and extension of recovery time. This makes daily activities such as showering very inconvenient. Second of all, these casts wrap completely around the extremity, blocking access to the skin. Normally, the outer layers of skin are constantly shedding, but now they actually have nowhere to go. This leads to very dry and scaly skin and can cause several hygiene issues such as foul smell. More seriously though, some casts can cause skin-related issues such as infections, rashes, and even severe dermatitis. Finally, traditional casts are very heavy, especially plaster ones. While fiberglass is lighter, it too can cause considerable difference in mobility. This is a specific case and it causes a very big disadvantage for people, for elderly and for kids. So with that being said, plaster casts only became popular in the 19th century. And since then, only other major innovation has been fiberglass. Modern material science and manufacturing techniques can greatly improve the experience. Since this is a medical technology, our priority will still be the proper healing support for the bone. For this reason, durability is essential. Decreasing weight is also another goal we wish to accomplish. Now finally, maintaining a personalizable aspect is important for mental well-being. In addition, we were hoping to add new features such as waterproofing, aeration, adaptability, and recyclability. We can now begin the design process and analysis. So, the team decided to focus on an improved design with the use of nylon, which can improve the recovering process. We chose nylon as it had properties that fit well with our many objectives. The following analysis will explain the differences between using the traditional cast and our new proposed design. To start off, durability is crucial, as our foremost priority is the healing of the bone. The cast must not break down during the recovery period. As seen here, the plaster of Paris has a Young modulus of 0.95 gigapascals. We can see that nylon is much greater, between 2 to 4 gigapascals. For the UTS, the plaster of Paris is around 36 megapascals, while nylon is also a bit higher, in between 45 to 90 megapascals. So as we can see, nylon is superior to plaster of Paris. If plaster of Paris has acceptable material properties, then nylon is more than capable of meeting the functional requirements. As for lightweight, we want to make sure that our cast is actually light. A walking cast strong enough to support an individual's weight can be made out of plaster and usually weighs between 10 to 15 kilograms. Comparatively, the same cast made out of nylon will weigh between 0.5 to 1 kilogram, much lighter. An important cultural aspect of casts is personalization. People often sign the surface and get colorful casts to make the awful experience of wearing an orthopedic cast more bearable. Nylon is also available in a variety of colors just like plaster. However, 3D printed nylons, especially in a honeycomb structure, won't allow the traditional experience of signing a cast. Fortunately, it does allow us to incorporate many designs into the surface of the cast without jeopardizing the integrity of the structure. So as mentioned earlier, traditional casts are not always waterproof. Those that are accompanied by extensive maintenance care as well as increased chances of skin irritation. Nylon's waterproofing can allow for a more normal daily routine. As discussed in the drawbacks, traditional casts can lead to skin issues. Our new cast uses the honeycomb structure as seen in this picture. That means the patient's fractured area is always ventilated, ensuring minimal skin irritation can occur. Finally, 6,600 tons of medical waste are produced in America daily. This number has been increasing at an alarming rate of at least 15% per year since 1992. Plaster is a non-recyclable material, and that is one of the biggest drawbacks of traditional cast. Nylon, on the other hand, is easily recyclable. The patient using nylon can return their cast once they are done, and it will be recycled. This way, we can help reduce plastic waste without compromising patient care. Let's now move on and talk about the manufacturing process itself, 3D printing. It allows for robust, quick, and custom solutions for each fracture. The medical industry is the third largest 3D printing market, with the latter continuously increasing at a rate of 30% since 2012. 3D printing technology with the combination of material selection can greatly improve the cast wearing experience and shows promise to improve the healing process for the wearer. A more unique solution can now be adopted to meet the needs of all individuals with fractured limbs. The process to develop the cast is outlined below. So first off, we start by the patient undergoing an X-ray and 3D scan. The doctor then receives data of scans and pinpoints location of the fracture. The software calculates pattern for best fit and optimal support and creates an algorithm that is then 3D printed. The cast is finally fitted onto patient while still in the hospital. So traditionally, the patient would wait another 3 days post-fracture to wear their plaster cast. With this new innovative technology, the patient can leave the hospital the day of fracture with the 3D print after only waiting for a few hours. The team built a table to showcase a relative metric comparison of the pros and cons of traditional casts and nylon print casts. As we can see here, the team opted for the weight distribution that seemed to be the most appropriate. This table was created based on a weighted decision matrix. As we can see, our suggested solution, nylon, was basically better for every single attribute except for cost, where it was a bit more expensive. For the overall, however, we can see that our suggested solution was much better. Based on industry survey, all candidates having experienced both types of casts opted for the newer, innovative form of technology. Now we will move forward for consideration and next steps. We understand that this is not a perfect solution, with many more components to address before distributing to the general public. The biggest drawback is the adoption and startup cost for this. 3D printers, especially ones for medical use, are much more expensive. and may not be affordable by every clinic as they can tend to cost around $250,000. Other adoption costs include software development and maintenance and training personnel. However, a majority of these are a one-time cost. We are confident that our proposed solution is superior to the traditional approach. As previously discussed, it mitigates many of the major drawbacks the old technology offers and improves upon existing features. Research still needs to be done to find the best possible way to reduce setup and maintenance costs. We hope our solution can make the experience of breaking a bone a little more bearable. Thank you, and I hope everyone's safe because of the whole COVID-19 situation. Thank you so much.